talk is about text classification with a combination of Apache Mahout and Lucene. It will be, as advertised in the program, it will be very, very introductory. It's just that talking to people, talking to colleagues, even talking to Lucene people, for most of these people, what I'm going to present wasn't particularly obvious. Also, for me, it was very clear how to combine these two technologies to get a benefit. So who am I to tell you something about classification with Mahout? I'm a software engineer at Nokia Maps. What we do, I'm personally located in Berlin in Germany, but there's also offices in Boston and in Chicago. What we do is mostly search on maps. Say, given a category, give me the most interesting POIs in a certain region. And that's also where we do lots of classification, like given a POI, tell me what is the category that's attached to this POI, is a correct one or not? Because some of the content that we get actually is user-generated content. So depending on how you set incentives for people to provide you details, you get more or less clean data. Apart from that, I'm a member of the Apache Software Foundation, co-founder of the Berlin Buzzwords Conference and the Berlin Hadoop Get-Together, and apart from that, also co-founder of Apache Mahout. So that's where my Mahout background comes from. I would like to know a little bit about the audience. I've heard that I scared people away at my first ApacheCon US by taking the microphone and giving it to everyone. So I won't be doing this trick today, but I still would like to know your background. How many of you have heard about RapidEye as a framework for machine learning? Okay, no one? Good. What about R? Okay, good. That looks very good. How about Mahout before joining the session? How many of you keep your hands up if you are using it in production? One guy, I want to talk to you after my talk. Now, what I really want to do to you is to motivate you to go to this web page. It's a wiki page. You can click the edit button and submit your success story online. Like with any open source project, we are always happy to receive user reports. It doesn't need to be only bug reports. We are also very happy to have you tell us which kind of problems you solved with the framework. Lucene clearly should be known in this audience. How many of you have solved a classification problem during the last few years? Okay, good. So when I'm talking about classification, I mean stuff like, given a place description and the location, should I send someone who's currently hungry to that particular place? Like, is this a place where this person can get food to fulfill his needs? Or it could be something, given an incoming stream of messages, like email messages, which of these are important for that user to deal with right now, based on what he interacted with in the past? Or very classic example, ham versus spam classification, incoming emails. Tell me which of these are just advertisement emails, which of them are scam, and which of them contain viruses, as opposed to the ones I really want to read and act upon. So to generalize, what we end up with is having a bunch of so-called examples, like text documents, for instance. And these have labels assigned to them. It could be positive, negative in the spam ham case, but could be important, non-important in the prioritization case. So our task will be, given these examples, train a model that will be able to predict a label of a new incoming unknown example. In the talk, I will focus mostly on textual data. So in the first step, we will go over finding and extracting text and removing noise from the text and which tools we can use for that. Second step will be about preparing text for classification and feeding it into a classification algorithm. And last but not least, we will have a look at how to do evaluation. So questions that we want to answer there is, what are good pre-processing steps? and how good will my classifier actually perform in the wild? Like, what performance can I expect? A little bit of terminology to start with, because if you read any classification literature, or if you look at the code base, you will find specific terms. First one is instance, sometimes also called example or item, but sometimes it's also just a row in a database. So these are the individual data points that you want to assign labels to. It could be mails in your inbox, it could be pictures from in a repository, it could be places that you want to reason about. Second term you will encounter is feature, sometimes also called something like attribute or signal, predictor, or the column in a database. Those are properties of your instances. In the mail examples, it probably will be words. In a picture, it could be, for instance, the color distribution. In essence, it's anything that helps your algorithm make better predictions. Can be pretty much absurd, and depending on your use case, can be pretty much obvious, like the word in your email. Last but not least, you will be talking about labels. So this is the desired predictions that your model is supposed to output. Like, for instance, the spam versus ham label in the case of email classification, or the urgent versus not urgent label. Now, we can actually draw a pretty picture out of that. Each example that you will encounter is characterized by a number of features. These features could be seen as a vector, and all these features essentially span an n-dimensional space. It's very easy to imagine having just two features, draw them in a coordinate system, and each instance will be just a point in that coordinate system. Now add a couple of 100,000 or 10,000 dimensions to that coordinate system, and you will know the way your classifier sees your example. Then you have a couple of examples available that you train on, which ends up being a matrix of features over examples. And the goal of your model will be simply to find a hyperplane. In the two-dimensional case, it would just, for instance, be a line that separates your two classes from each other. That's all that happens. So essentially, there's not a lot of magic going on. The trick is to find the correct feature combination and to use the correct classification algorithm for your problem. To give you an example of what correct feature choice can influence, I've got a friend who worked on an email spam classifier. He spent days and weeks in order to tune the algorithms that he had, in order to tune the weights, exchanged the algorithm, exchanged the training, and came up with an accuracy of roughly over 90%. So he took this implementation, took it to the engineers who knew what the emails on the servers really looked like. He talked to them, he told them, like, these are the features that influence the prediction most. And they were like, okay, well, there's this one thing, this one property that could also be relevant, and there's another one, and there's another one. So what he did was to sit down and essentially compute an Excel sheet that would output the features by feature weight, like the most important one on top, and would allow the engineers to iterate quickly on the feature combination. By the end of doing that, he ended up using a very simple, very stupid algorithm and a rather tricky feature combination, but ended up with having 100% accuracy, like on his training example at least, perfect accuracy. So for him it paid a lot to make it easy for the engineers to iterate on these features, as opposed to spending hours and days in the lab working just on the theory behind the algorithm. Another example that demonstrates some of the trouble you will run into, namely the trouble that your implementation will be a moving target, is another guy working at another company, again on ham versus spam classification. They based their email classification only on the text. And after rolling it out, it went very well, up until the morning when the sysadmin came to the office and all hard disks were totally full. So the admin went and looked what happened to the email system. Well, suddenly those spammers had gone out and posted completely non-suspicious text in the email, included the advertisement in a tiny little GIF that was attached to the email, and put it like text into this GIF. So the next iteration of the algorithms or of the implementation suddenly also had to understand how to parse pictures. So you will always have to reiterate if you are working in this kind of space. When it comes to Mahout, it offers you your typical problem solutions. It offers you documentation on working parameter configurations. It does have decent scaling properties, but there are other tools around that make it easier to play around with with algorithms and with feature generation. So we don't come with a graphical user interface so far, but are just libraries that you can use. If you would rather plug and play many different algorithms or plug and play with different feature generation options, you might want to go for a first exploratory iteration with stuff like Vecca or with RapidEye, RapidMiner that I mentioned earlier. Some of these even integrate Mahout as part of their workbench. So that's probably nothing that you're going to ship to production, but it's mostly something that you will use in order to understand your problem and your data. So after having the terminology out of the way, let's take a look at textual data. What does it look like? Well, your typical text document isn't only plain text. If you're really, really unlucky, and most of us tend to be unlucky when dealing with text, especially in-house, those texts come in a binary format. It may even be a proprietary format where you don't understand the parser exactly. Even if it is plain text, it may be dirty HTML that doesn't validate. It may contain CSS. It may contain advertisements that you may not want to use for your classification task. It probably will contain navigational links that you want to filter out. It probably will contain images that you may want to use or not use. So your first step will always be to extract the full text. Like remove advertisement, remove all the noise and navigation from the page. You don't need to reinvent the wheel here. There's projects that do that very well. One of them is Apache Tika. Comes with a lot of parsers, not only for HTML, but also for other formats. There's something like Boilerpipe that can extract full text from your document. There's something like TechSoup to deal with not quite clean HTML documents. So you can just use these projects in order to speed up getting started with your project. So what you've got now essentially is a piece of content, so it doesn't contain all the navigation and noise. What you need to do now as a second step is to convert it into something that a classifier can understand. So the first step will be to take this full text content and split it up in words. Okay, so text obviously usually consist of words. You can also call them tokens. How does it help with vectors? We just assign each of these terms to, say, one dimension in our vector, and then we have our document represented. Okay, anyone have in the past dealt with encoding issues? Anyone with Chinese, Japanese languages, with the problem of a New York versus New York as a city? Anything with Go the verb as opposed to Go the game? You really don't want to go for reinventing the wheel here. You don't want to go and write your yet another whitespace tokenizer. We are at the Lucene conference. Obviously, what can we do? We know how to transform text into tokens already, right? We know that Lucene does have an analyzer class and that it does have many different ways of tokenizing text. It's very easy. So there's people who've dealt with tokenization, with stop wording, with different encodings, with broken encodings. And all of these are extensible for your own needs, so you don't need to start from scratch, really. So now we have terms. How do we turn them into vectors? Let's go back to a two-dimensional vector for a minute. Imagine that all our documents only really have two terms that are important. One of them, or like really two phrases, one of them being sunny weather, the other one being high-performance computing. You can easily imagine that terms that are roughly in the corner where the green cross is have nothing to do with HPC, but a lot with sunny weather, so that kind of could be weather forecasts. The blue cross over here probably has something to do with scaling issues, but not so much with weather prediction. If you go to the red cross, you will probably end up having something that talks about both HPC and weather prediction. So it may be something related to an algorithm that computes climate models or something like that. Now in the real world, of course, you don't have only two terms or two phrases in your documents. You have many more. You may have one dimension for each word. You may even have, for documents that you haven't trained on, new words flowing into the systems that you need to somehow deal with. So one way to deal with this is to imagine an n-dimensional feature space. Each word in the text is being hashed into one dimension. The n is smaller than the total number of words in your dictionary. So this way you can match words into hashed IDs. So you have just a limited number of dimensions. You have set limited, and you don't need to know in advance the complete dictionary. Of course, with the simple, if you set the dimension to 1 if the word exists, and the dimension to 0 if it doesn't exist, you don't account for the number of occurrences. So you may want to take the term frequency into account. If you take only term frequency in the current document into account, you don't respect that some of the words are very common in many documents, like stop words, for example. So you may want to go for stop wording, of course. Again, here you have a hard gap between what is a stop word and what is not a stop word. What you can do as well is do something like TF-IDF scoring. That's also available in Lucene for scoring. So that here terms that are very frequent in the whole corpus don't influence the vector as much as words that are seldom in the whole corpus, but very frequent in my current document. Also, for these conversions and for this complete feature hashing, you don't have to come up with your own implementation. In Apache Mahout, there is a so-called Lucene text value encoder that can take the output of a Lucene analyzer and turn it into a feature vector encoding. And there are similar classes that you can use in order to generate features out of numerical values, etc. So you don't need to think about how to generate the vector, but you just take a look at the implementations that Mahout provides for you and go from there. So in the end, your classifier will simply see dots in vector space and will try to find a linear separation. And again, you can use, for instance, a class called online logistic regression and just feed the just generated vectors into it. You don't even have to write them on disk. You can do that in process, but you can also store them on disk because all the vectors in Mahout implement a writable interface. So you can read and write them from disk as you want. And this algorithm will then train a model, which you take, push to production, load there, and use in order to predict new instances. So what your workflow will look like is something like that. You get text from anywhere. You feed it into something like Apache Tika in order to get really the plain text out of it. He takes a full text, put it into an Lucene analyzer in order to split it into terms and tokens. He takes that token stream, feed it into a Mahout feature vector encoder in order to generate vectors from these tokens. He takes a vector, feed it into an online learner in order to train the model, and there you go, you're done. Well, not quite so. So far, we haven't looked at the quality of our implementation. What I will show you is some general ways to approach the problem of how do I judge quality. In the end, the way you judge the quality of your classifier will depend again on your use case, because making a mistake may have different costs associated with it, depending on which mistake you make. Imagine the spam versus ham classification. It may not be as bad seeing a spam email in my inbox as it is to miss the Lucene Revolution talk confirmation email if that goes to my spam folder. So this time there's really two goals. One of the goals is find out whether I use the best model parameters. There's usually different weighting schemas, different feature extraction schemas, different features that I can use, different combinations that I can use. So how do I come up with the best combination? And the second question to answer is how good will my model perform in the wild? If I deploy it now, I want to tell my manager, or at least my users, what is the likelihood that a spam, like a ham email, ends up being in the spam folder. I want to have at least a gut feeling for that. So I will have multiple iterations for tuning the model, and for experimenting with tokenization, for experimenting with feature vector encoding. And in a final step, I will want to compute how good that model will be. So we always start out with a set of examples. They all have labels assigned to them, like in this case, positive and negative. And based on that, we will want to make predictions on how good our implementation is. Now, what I have seen people do is to use the same data for training and testing. Essentially, that is the same as giving the exam out to the student before the actual exam happens. So the student will know the answers beforehand. That's a little bit like cheating, and especially it's highly optimistic. So you won't know how your model will perform in the wild, how it will generalize from seen data to unseen data. So this is a great, huge, don't do that, never, ever. Next typical thing is use just a fraction of your example data for training and set some data aside for testing. Clearly, this is pessimistic because you don't use all of your training data for training. So your model won't have seen everything. And your result might depend on which data set you've set aside. Like if there's some specific characteristic in your test sets that you've never seen in training, just because of the way you split those two, the model will perform better when trained on everything and shipped to production. So the typical way to deal with this kind of problem is to do kind of a round-robin training, also called cross-validation. So you partition your set into n fractions, train on everything, leave one fraction aside. You do it again with the second set fraction and again until you're done. So this way you ensure that at least you've seen everything. You can average over it, and you can make at least a prediction of how good you will be on average plus standard deviation, which gives you a better idea. Of course, it's still slightly pessimistic because for each iteration, you only see so much of the training data. Now, what you will typically do is that you have multiple iterations where you tune your parameters. So you first train your model, you come up with this prediction of how good the model will be, And then you think, maybe I should put the weights a little bit different, or I should put feature generation slightly different. If now you repeat the process from above, you cannot any longer use the predicted performance as the ones that actually will be encountered in production, because the more often you do that, you will again have the student who knows the exam before the actual exam problem, because essentially what you do is to manually overfit your parameters. So if you can't do that, what we will do now is to come up with one set for training, one set we use for parameter tuning, and one set we use in order to predict how good our model will be in production. And we can again come up with this cross-fault validation setup where we iterate through all sets. It will be a little more pessimistic than what we did before because we use less data for training. It may again, if we don't do the cross-fault validation, it will again depend on which data set was set aside. However, this kind of setup is the only way you can reliably predict how your model will be if you do parameter tuning in between, which I highly recommend, because the final performance definitely depends on your knowledge that you put into features. There are some standard performance measures, because now we've only talked about the process, we haven't talked about the actual metrics. There's some standard performance measures. You may want to tweak them according to your cost model. In order to explain these performance metrics, imagine again your training set and what your classifier does to it. So these, assuming that this is the correct label, these are all the correct, wait a second, where are we? Yeah, so the green ones are the correct ones. Everything down here is what was labeled before as correct, and where the classifier said, yep, that's the correct example. The one up here is everything that was labeled negative before, and where our classifier also said, okay, that's a negative example. Apart from that, we have two sets. One of them being it was labeled as correct, but our classifier said, that's incorrect. The other one being that it was a wrong example, but our classifier said, yep, that's a correct one. Based on this notion, we can define something called accuracy. Accuracy is just the true positive and the true negative over everything else. Now, so this is a very typical thing to do as a first step. However, what happens if you have a training set where you have 99 negative examples and one positive one? If you have a very dumb classifier that always says negative, you will end up having an accuracy of 99% without having done any work. So that doesn't help me really if the distribution is skewed. There's another pretty standard thing to do, which is called precision and recall. Here you have essentially two forces going in two different directions. There's precision being true positive over true positive and false positive. Like of everything that was in there that could possibly be positive, how much, no, of everything that I predicted as positive, how much was actually positive. And recall is the other end. How much of those that I could have retrieved did I actually retrieve as positive? So if you wanted to optimize for recall, you could just predict everything to be positive, but that would give you a penalty on precision and the other way around. The problem with that is if you, for instance, compare different algorithms, you probably will have to define a threshold after which you consider an example to be positive or negative. So the comparing precision and recall always depends on that threshold, depending on which trade-off you made. There's one thing that's threshold independent that you can use, and that's so-called receiver operator curves. They come from submarines, where people wanted to judge radars across different vendors. So the goal for the radar was to identify missiles coming to the submarine, but to not identify fish swarms as missiles. So what they did was to take a bunch of fish swarms and missiles and to tell an operator to classify them as fish swarm or missile. They then ordered these examples by probability of this particular item being a missile. Only after the effect, they revealed the actual labels. Now, in an ideal world, you would want to have a classifier that is first all positive and then all negative examples, because there you can find a perfect threshold. In the real world, you will end up having probably something like that. It will first give you a few positive examples, maybe a negative one, positive again, and so on. In the worst case, your classifier will end up sorting your examples like this. So they are totally random, and you can do whatever you want to your threshold. You won't get any better than random. In a perfect world, you want the curve to first go all the way up and then all the way right. Or actually, it is also okay if it first goes all the way right and then all the way up, because then you just switch labels and you're done. Now, comparing curves isn't quite as easy, so you can compute the area under the curve. The bigger that area is, and especially if it's bigger than 0.5, the better you are. So that's like one standard way of judging your prediction performance. Of course, your mileage may vary. Researchers I've talked to mostly worry about file format conversion before they worry about classification accuracy. In production, the problems you will encounter probably relate to how does the data flow from its source to my implementation? How do I store, load, monitor, and update my model? So Mahout can help you here to some extent, because it comes with efficiency realization options. There's one caveat. The file format for the models in Mahout is Mahout specific, so you will probably not be able to load the model in some other data science tool. There have been some requests to rely on a standard PMML implementation. So far, requests haven't been strong enough for some of the committers and users and contributors to stand up and actually implement it. Hadoop does come with a command line interface, so you can run your job on Hadoop clusters. Large parts of the framework also come with decent Java APIs that you can simply integrate in your software, so you don't need a Hadoop cluster running. And speaking of Hadoop clusters running, Hadoop is very cool. And it's also very good if you can say, my other computer is a data center. It's kind of nice for a developer. But there's a saying in Germany, which is, don't turn a mouse into an elephant. So unless you really have a scaling problem, I would advise to use the non-distributed version, really, because it's much more easy to handle. And usually the part that needs a lot of processing power is the training anyway, not so much application in production, because this for classification usually can scaled out linearly anyways. As with anything, Mahout isn't a silver bullet. It's just a solution for how do I turn Greek symbols into working Java code. So it provides you with production-ready implementations. However, the domain knowledge is still on your side. See, how do I convert my particular instances into vectors? That's a problem that you will have to solve. We can help you if you give us a Lucene analyzer or if you give us text. However, that doesn't mean that Mahout itself is constrained to classifying only textual data. It just means that if you have different data, you will have to come up with a mapping from the data to vectors. Of course, it does have decent out-of-the-box performance. However, it's clearly not something like a pig or hive for machine learning, so you will end up writing Java code to glue all of that together. One kind of message that I usually tend to give people is to not treat it as a black box. First of all, knowing your data helps a whole lot with coming up with sensible features. Knowing what is important, which properties are important, which properties influence a classification decision, that really makes a difference. So spending time there, understanding your data helps you in the long run come up with better results. Also, don't be afraid to take a deeper look at the algorithm that's there. Don't be afraid to ask questions on the mailing list. People tend to be very open and answer these questions, in particular if you give details on your use case. So today we've looked at a tiny little box, and the tiny little box is over there. That's only classification. The framework itself can do more. It can do stuff like recommendations, like given a database of users and interactions with products, for a given user, give me a recommendation for an item that this user should either watch if it's a movie, or buy if it's a product, or look at if it's a picture. It can do stuff like sequence learning. Essentially, it's all based on decent math libraries and collections libraries. And there's a whole lot of implementations that are Hadoop ready for you to use. If today wasn't challenging enough for you, I've got a whole bunch of other resources that you can look at. There's a couple of libraries that could be helpful, like for instance VopalVapid for online learning. LibLinear is used by many people. If you want to get more information, there's a book out there by Manning on Mahout in action and taming text. There's a great machine learning course by Andrew and G out on Coursera if you want to dig really deep. There's a whole reading list on our wiki that you can check out. There's a few other frameworks that you might want to take a look at. For instance, Weka, as mentioned earlier, is a little bit more graphical, RapidEye as well. R, if you want to do much more data analysis before feeding your algorithm with vectors, like coming up with statistics and nice visualizations. If you want to get your hands dirty now, but you don't have the data, there's even a solution for that. There's a site like Kaggle.com. And also on the Mahout wiki, we do have a list of data collections that you can base your algorithms or your implementations on. So if you want to start hacking now, I would advise you to head over there. There's other conferences where you can find interested people, some of them like more hacking-based, more engineering-based, like ApacheCon, O'Reilly Strata, Berlin Buzzwords, or Lucene Revolution, obviously. But there's also a couple of scientific conferences. Even if you don't go there, these papers tend to be interesting to check out, not only for the algorithm side, but also for the evaluation side. You will find many other metrics, including advantages and disadvantages, and you will find many more feature generation algorithms. So this is my invitation for you to get started today with the right tools instead of reinventing the wheel yet another time, even if it's just for something as simple as tokenizing text. It's my invitation to discuss these ideas and problems online, because clearly there's a lot of people out there who probably have tackled the topics that's similar to yours, and at least the Mahout mailing lists tend to be very friendly. It's also my invitation to go out, discuss these ideas and problems in person, either if you go upstairs for a coffee after the talk, or even next year in May, come to Berlin and visit me. However, if you do all that, there's a very, very grave warning that I have to attach, and that is that at some point you may end up being on the slide as one of the committers of those projects. Like Grant Ingersoll told us earlier in his keynote speech this morning, It's actually easier than you think to end up on this slide. It just takes a couple of patches, and those don't actually need to be coding patches. It also could be documentations that you add to the project. It could be examples that you write. It could be Maven build structures that you fix. It could be build fixes that you attach. It usually doesn't take very long to get you there, but it takes really, really long to get you down from that slide. Because at Apache, we have that saying that merit doesn't go away. And we tend to do a very good job at motivating people to come back again and again once they've started contributing. So you may end up spending your weekend at conferences or coding up for Mahout, for Lucene, or for different projects. Just for your reference, I've put the mailing lists up here. So if you're interested in solving hard problems, if you're interested in being part of a lively community, maybe wearing one of these committer shirts next time around, just join these lists. They are always happy to receive bug reports. If you attach a test to the bug reports, it's even better. If you attach a fix that fixes the test, that's very much appreciated, but it doesn't have to be. Just telling us there's something wrong is okay as well. New features, new patches, documentation, code examples, all very welcome. And with that, I'm looking forward to see any one of you subscribe to these or to contribute to these, and I'm open to take questions. Yeah. Do we have a microphone?
I'll just speak out loud. For the tokenization part, you mentioned you use Lucene for tokenization and analyzers. Yeah. Do you have anything for part of speech tagging which is in line? Or do you have plans to have something like that?
So currently, the question was for tokenization, we use Lucene. For part of speech tagging, I would advise to take a look at something like OpenNLP, which is another project. It isn't integrated just as well as the Lucene stuff right now, but they do have the algorithms, I think, for POS and also for named entity recognition, like given a text, give me all the cities, etc. So that's what I would look at first. So comparing SkiKit to Mahout, both of them can run on a single machine. I haven't seen Mahout blow up completely so far. It could be because of my data isn't large enough. Especially for the classification stuff, that's usually fine. The stuff that tends to blow up is when people do clustering, like k-means, with thousands or 10,000s of clusters. That's one of the cases where it blows up. The other thing is if you do recommendations, and you have like a user that has rated each and every item, like essentially a spammer, that also tends to blow up. So there you have to do pre-filtering, take a random sample out of the items that the user has rated. That usually works out well.
Yeah, in my case, it was text classification specifically.
So for text classification, I haven't seen it. So the logistic regression itself is online regression, so you only see one example at a time, and you can iterate over as much text as you want to. So it really only keeps the model in memory, and model essentially is just vector plus weights, and there not a lot can happen.
Yeah, but I mean it's a good motivation to try Mahout and
yeah.
these kind of prototyping tools.
It's nice to take a look at these prototyping tools if you start, because they are reasonably well integrated, but you should be aware of the fact, like it's the same happened to me when using Weka. Depending on which implementation you use, essentially Weka is still open source, but developed by a bunch of researchers, and each of them contributed one of the algorithms, so depending on who contributed, you will end up having different quality. So the same happened for me with Weka, where depending on which implementation I choose, and depending on which algorithm it implemented, it would blow up or not. So it's nice for exploration. It's nice for getting a feeling of what machine learning is. It's nice for getting a feeling for classification, but it's nothing I would recommend to go to production with or to go large scale with. You should always keep in mind that you probably will have to revisit your decision.
We're using k-means in Mahout, and we have noticed some problems with higher dimensions. So is there any workaround that you're aware of so that we can do k-means with many dimensions? And another question that's related is we're using lassos, I believe, for the SVD. Have you seen any problems with the stochastic version of that?
As for the latter version, I would recommend you going to the user list and to the dev list, because there I'm really the wrong person to answer that question. About the former one, there's a couple of things. How many clusters do you want to generate with k-means?
Probably thousands.
You may want to look at the streaming k-means implementations that came out with 0.8.
One of the problems I see with the general ML approach is, well, how do I get the general idea about the size of training data you need? Is it in thousands of 10,000s or, you know, hundreds of thousands of examples? Is there any methodology, just a, you know, gut feeling? And
the typical thing that, like the first thing I would look at is to look at something called the training curve. Like, over time, how many mistakes do I make when increasing the training set size? If this stabilizes, then I know that I've got enough training examples. It usually depends on how hard your classification task is. If it's, is that a scientific document about mathematics, or is that a news article that's clearly easier than is that a scientific article about computer science / machine learning, as opposed to a computer science article about a different branch. So there you may need more training examples.
no, the point is that, well, there's no easy way to get the idea early on, because that translates to know the cost of the project, and you have to calculate it in early on.
Yeah. Mm. So you will probably end up launching like a prototype that's time boxed, see how far you got there, and do your estimate.
Thanks. Isabel, do the classifiers now all use a standard format for the input, or is it still, do you have to generate an input for each specific classifier? Because I think until very recently, you had to, there was no standard input.
So I would generally recommend to go for the SGD classification because it has a decent Java API and a decent input format. I'm pretty certain that at some point we streamline the input for the classifier. I wouldn't put my hand on fire and promise to you that all has been streamlined, but I'm pretty sure that on the classification side we are rather safe there. So this should be the same. If it isn't, then open a bug report.
Okay, I thought there was a Jira for unifying all this already.
So I'm aware of a Jira for streamlining the clustering stuff, but not so much for the input for the classification. But it could be that I'm just not remembering one of these issues.
Right, okay. Okay, thanks.
So apart from that, I will still be around for all day. If you have any other questions, catch me upstairs or around here, and I'm happy to help you. Thank you.